Morning class. It's homework review 4. I'll be efficient with this because I know that this is a very busy week for many people. So let's get to our homework. We had 3 parts to this homework, and first 2 were t-tests of each of a different variety, and the third was in Anova Problem. So let's figure this out. Part 1. Demographers believe that sex affects the age at which one begins their first marriage. Interested in this idea, you sample 50 adult men, 50 adult women, all currently married. Find that the average age at first marriage for men is 29, standard deviation of 4.5 years. The average age at first marriage is 27 years for women, with a standard deviation of 3.3. Now, can we say with 95% confidence that there is a difference in age at first marriage between these two groups in the United States? So the first thing that I looked for here to figure out what I wanted to do, I put a box around the words "a difference," and I did that because I am going to have to, with any t-test, make a decision between a one-tailed test, and if so, which direction, and a two-tailed test, which in this case, we have a two-tailed test. So moving to the actual steps here, we always have to do all 6 steps of the hypothesis test. So step 1, I had to decide which sample is going to get the notation of 1 and which sample is going to get the notation of 2. Now, because I had a two-tailed test here, right, all I care about is a difference. It doesn't matter how I arrange this. I decided, because I like to keep things positive rather than negative, I decided to keep the larger sample mean as x bar 1 and the smaller sample mean as x bar 2. So men are going to be the first sample. X bar 1 equals 29, S1 equals 4.5, N1 equals 50. And then for the second group, that's going to be women, X bar 2 equals 27, S2 equals 3.3, and N2 equals 50. I also wrote down here no direction. That tells me that I am doing a two-tailed test. And that's really all I need for step 1. Moving on to step 2, since this is a two-tailed test, the hypotheses become a little bit less complicated. So when I say there is a difference in age at first marriage, a difference, well, that can be a difference in which the first mean is greater than the second mean, or that could be a difference in which the first mean is less than the second mean. Either one of those is still going to be a difference if it proves to be significant. So for a two-tailed test, my null hypothesis, or what we refer to as H0, that is mu1 equals mu2. That would be the only situation in which there isn't a difference, if these two things are the same thing. H1, my alternate hypothesis, you'll remember this is the thing I'm trying to demonstrate. Mu1 does not equal mu2. So I draw the equal sign with the little line through it, and that indicates does not equal. Steps 3 and 4, I need to set my alpha level. Well, 95% confidence, therefore 0.05 as my alpha. And then for my degrees of freedom, I am going to use the formula for the two means t-test, where I do n1 minus 1 plus n2 minus 1. So both n1 and n2 are 50. This is an equal n formula. So degrees of freedom is 50 minus 1 plus 50 minus 1. That equals 98. So 0.05 alpha, two-tailed test, 98 degrees of freedom. You should have identified a critical T of 2.00. And then you'll notice I put in parentheses here plus or minus. Since this is a two-tailed test, I am going to need to calculate a T that is either greater than positive 2 or less than negative 2. If it falls beyond, we're either greater than the positive version of this or less than the negative version of this, that will allow me to say I reject the null hypothesis with 95% confidence. Step 5 is where our money is made, though. All that's prep work. Let's actually make some money here. I first need to calculate S of x bar 1 minus x bar 2, and then that will go in the denominator of my T formula. S of x bar 1 minus x bar 2 is the estimated difference between the standard errors of our two hypothetical populations here, males and females. And the formula, you will remember, I spent a lot of time harping on this in class. it requires you to input variance. So if you're given standard deviation, you must convert it to variance by squaring the standard deviation. So I am going to take the square root of S1 squared divided by N1 plus S2 squared divided by N2. So this once I input my stuff here, this becomes 4.5 squared over 50 plus 3.3 squared over 50. That becomes the square root of 0.405 plus 0.2178, and that equals 0.7892. That is my estimated difference between the standard errors. So T now, x bar 1 minus x bar 2 over S of x bar 1 minus x bar 2. So that becomes 29, that's x bar 1, minus 27, that's x bar 2, over 0.7892, which produces a t value of 2.534. If you came up a little different, like just a touch different on your rounding, I don't see that as a big deal. Is 2.534 greater than 2.00, positive 2.00? It is. Therefore, I reject the null hypothesis with 95% confidence, and I conclude that there is a significant difference between age at first marriage between males and females in the United States. How do we do out there? Hopefully pretty good. Moving on to the second one, I'm going to make even a little more money here. To better understand gendered earnings, we want to sample 100 men and 125 women. Notice how I circled those. That is important for dictating whether I can use the equal ends formula for a t-test or the unequal ends formula for the t-test. These ends do not look the same to me. Therefore, I have to use the unequal ends formula. We find average starting annual salaries of $28,200 for men with a standard deviation of 1,200 and $24,100 for women with a standard deviation of 1,500. Can you conclude with 95% confidence that men do indeed make more money than women? All right, stop for a second. More. Okay, I have a directional hypothesis here. I don't just care about any difference. I care about one specific direction of the difference. So this is going to be a two means, one-tailed t-test with unequal ends. Because I am looking for one group to be greater than the other group, that's the hypothesis I'm testing, I am going to make the larger sample mean x bar 1. The smaller sample mean then, of course, has to become x bar 2. And by doing that, that ensures that my observed t, my calculated t, will be positive. And I will then compare that to the positive critical value. So arranging these things, like most of the things you need to do to get the right answer come in just how you arrange these things. So step 1, what do I know? X bar 1, 28,200. Although I'm actually going to do something, hopefully clever when I actually calculate this, and we'll get to that in a second. I'm not actually going to use those numbers because they're huge. I'm going to reduce them, and I'll show you what I mean by that. So I will take 28,200 as x bar 1, S1 is 1,200, N1 is 100. X bar 2 is 24,100, S2 is 1,500, and N2 is 125. Now, since I have a directional hypothesis, I have to actually take some care in what I am producing here for my hypotheses. So you remember, can you say that men, with 95% confidence, that men make more money than women? More. Therefore, to make more money than women, mu1 must be greater than mu2. So what's the inverse of that? H0, mu1 is less than or equal to mu2. H1, mu1 is greater than mu2. So that alternate hypothesis, H1, is what I'm hoping to find evidence for. So steps 3 and 4, we'll get through this quickly. Alpha level, 0.05. I picked that because I was asked with 95% confidence. DF, n1 minus 1 plus n2 minus 1. That equals 223 degrees of freedom. And I'm putting all of this in one tail, a one-tailed test. So the critical T for 0.05 alpha on a one-tailed test with 223 degrees of freedom, that gives me a critical T value of 1.645. My value, what I actually calculate going forward, has to be greater than 1.645. So getting to the meat of the problem here, I have to do a three-step process here. I first calculate S squared P. Then I put that into my formula for S of x bar 1 minus x bar 2. And I then put that in the denominator for my t-test. So S squared P, 100 minus 1 times 1.2 squared plus 125 minus 1 times 1.5 squared. And that is over 100 minus 1 plus 125 minus 1. Do your order of operations there, right? Start with the exponent first, then go to the multiplication, then do the addition, and finally at the end the division of the denominator into the numerator. And this gives me 1.89. Wait, 1.89? Notice what I did here. I was operating with really big numbers. Once you square, do you know what happens when you square a number? It gets a lot bigger. And when it's already a big number, it gets a fuck ton bigger. So notice what I did here, 1.2 and 1.5. For everything I do here, I am going to now take that 28,200, the 24,100, the 1,200, and the 1,500. Notice how there's two zeros on the end of everything. I'm just going to take those away and make this 28.2, 1.2, 24.1, and 1.5. Essentially, what I'm doing is moving the decimal point 3 places to the left for all 4 of my values here. Because I do that in a mathematically consistent way, I'm good. I'm covered. And what that will produce, right, using 1.2 and 1.5 as my standard deviations, I have to square those in order to turn them into variance. S squared P is 1.89. That then goes into my S of x bar 1 minus x bar 2 formula, so I get the square root of 1.89 over 100 plus 1.89 over, that actually is supposed to say 125. I apologize for the typo. We can all make a mistake, can't we? And that equals 0.1844. That I'm positive is correct, actually. That then goes in the denominator of my t formula, and I have 28.2 minus 24.1 over 0.1844, and that gives me 22.23. So I asked the class, is 22.23 greater than 1.645? Yes. Therefore, I reject the null hypothesis with 95% confidence and conclude that there is a significant, that men do indeed earn higher starting salaries than women. Yeah, the gender gap is a real thing. So we reject age 0 here. Good for us. Moving on to the Anova problem. Let's make this a little bit bigger. All right. Here's what do I have here? I have a stress level problem. We have 15 students, or 5 students, pardon me, but they are sampled at 3 specific data points. Therefore, I am doing an Anova problem with 15 overall observations. The mistake that might have been made here is to think that n is 5. No, n is 15 because each student is sampled at 3 different times, giving each student 3 data points, giving the total group 15 data points. So I'm going to have 4 means that can be calculated here. So let's actually go through steps 1 through 4 first and then go to the meat of the problem. Step 1, state what you know. X bar 1, that's going to be week 1. That's a mean of 4. X bar 2, that's going to be midterms. That's a mean of 8. X bar 3, that's finals week. That's a mean of 13. I put all 3 of these together, and my grand mean, or X bar total, is 8.3. I'm also going to write down an N of 15 and a K or group size, or a number of groups of 3. My hypothesis, the null for an Anova problem is always that all of these group means equal one another and also equal the grand mean. So mu1 equals mu2 equals mu3 equals mu total. The alternate hypothesis, these things don't equal each other. Mu1 does not equal mu2, does not equal mu3, does not equal mu total. So using the alpha characteristics of 0.05, I was asked with 95% confidence, and a degrees of freedom of 2, 12. How did I get that? Well, df1 is n minus, df1 is k minus 1, so that's 3 minus 1, and df2 is n minus k, so that's 15 minus 3. The degrees of freedom, or the critical f corresponding to a 0.05 alpha and degrees of freedom of 2, 12, that gives me 3.88. ANOVA's no-tailed. Therefore, I will be able to reject the null hypothesis with 95% confidence if I get a value of f that is greater than 3.88. All right, let's get to it. The first thing that I wanted to do here was to calculate my sum of squares within the group. And so I do that by subtracting the group mean from each observation, squaring it, and then summing it. I do that for all 3 groups and get the total summation. So the sum of squared deviation, the sum of squares within the group for week 1 is 22. The sum of squares within the group for midterms week is 18. And the sum of squares within the group for finals week is 14. Add those up, my sum of squares within the group is 54. Not a very high number. Now, if we look at sum of squares between the group, that involved taking each group mean and subtracting from it the grand mean. The grand mean was 8.3. That's x bar total. So group mean minus grand mean squared and multiplied by k. K for all 3 groups here is 5. So that gives me sum of squares between the groups of 92.45 for week 1, 0.5 for group 2, the midterms group, and for group 3, the finals week, 110.45. Sum those together, and my sum of squares between the group is 203.3. Okay, let's stop and take stock here. We have our sum of squares between the group of 203.3. We have our sum of squares within the group of 54. What we are looking for in an Anova problem is to reject the null hypothesis by finding out that the majority of variation is happening between groups. That means that the group itself is responsible for what you're seeing. So now I have to normalize for the sample size. I do that by dividing by degrees of freedom. So mean squares within is 54 divided by 12. That is the sum of squares within the group divided by the degrees of freedom within the group. That gives me a mean squares within of 4.5. My mean squares between the group is 203.3 divided by 2. That is the sum of squares between the group divided by the degrees of freedom between the group. And that gives me 101.65. On to my next page here. F, then, the very last thing we have to do, 101.65 over 4.5, and that gives me an observed F of 22.58. So I asked the class, is 22.58 greater than 3.88? Yeah, I'd say so. Therefore, with 95% confidence, I reject the null hypothesis and conclude that you're all about to be really stressed out next week, right? That there is a significant relationship between time of the semester and student stress levels. Reject age 0 with 95% confidence. Now, the problem here did not specifically ask you to compute Eta Squared. But we can do it anyway, right? Maybe my suspicion is that many of you probably did just out of habit of seeing it in your notes. So yeah, I'll just show you what that is. If you didn't do this, it's not going to come out of your grade. But yeah, eta squared is the percentage of all variation that can be attributed to between the group differences. So let's go back here, right? We have our sum of squares between, our sum of squares within. What we're doing here is the sum of squares between the groups divided by the total sum of squares. So that is 203.3 divided by 257.3, or 0.79. So not only do we reject the null hypothesis with 95% confidence, I can also say that 79% of total variation in student stress levels is due to the time of the term. And then we get a little smiley face because we finished the homework well. So anyway, that's what I got for you today. If there are questions or concerns, don't hesitate to let me know. And I wish everybody a great Elkin Isaac day tomorrow. Take care. Bye.